seconds before the camera is about to run out, I'm going to say, okay, well, next we're going to start going over the answers to the exam. Then it's going to turn off. And have everybody freaking out at home. Let the video stop. Okay, anyway.
I think I have a really ugly function, but I think it'll work.
Oh, you're already creating one. So Cheyenne must think that they are homeomorphic.
Yeah. Yes.
Okay. Does most of you think that these are homeomorphic spaces? Mm-hmm. Okay. That would be correct. Now, be careful. Could I say that the real numbers are open, and this is an open interval, therefore they're homeomorphic?
No, because this is just one.
That's just one set here and one set there, right? And actually, the whole space is always open. Of course, the real numbers are open as a subspace of themselves, and this, even if I could have. If that reasoning was okay, I could have done this. And I could say, oh yeah, they're homeomorphic because this is open and this is open. Not a good justification, right? Because openness is only relative to the space that you're working within. Of course, this is open within itself, but it's not open as a subspace of the whole R, right? So you have to be a little careful about that. When you're thinking about topological properties, you should be thinking about things like compactness, T0, T1, T2, T3, T4, regular, normal. What else could we be thinking of topologically speaking? Convergent sequences have a limit within the space. We use that one. Connectedness, that kind of stuff. If one space has 17 open sets and the other space has only 16 open sets, well then they're not homeomorphic, right? They have to have the same number of open sets and closed sets as each other. All of those kind of things have to be true. Okay, but most of you are agreeing that these two spaces are homeomorphic. And so what I would want would be, let's just call this capital A and capital B. So a function from A to B via... Yannick, do you have an idea? No. What function we can use? No? Who has an idea besides Cheyenne, because she's so excited? I'm going to contain her excitement for just a minute. Try to think of a function that will work. Or there's another thing you can do, which is you could come up with an intermediate space. You could say, well, I don't want to directly explain why this is homeomorphic to this. I'm going to instead explain why this one is homeomorphic to something else, which is then homeomorphic to this one. So you could also, because remember, homeomorphisms are transitive. If you compose two homeomorphisms, you just get another homeomorphism again, right? So that would be another idea. Jason, do you have an idea?
I'm kind of thinking for a function here, we kind of want to map probably like 0 to -7 for our 0 to -infinity, possibly 0 to infinity to our 0 to -7.
So positives to positives and negatives to negatives?
Yeah, so we just need to find a way to constrict our infinity to within 7, possibly.
Right, so you need a function that somehow
so you're using,
kind of
what was
shrinks.
it, proposition where you can split them up and show that it's
proposition?
Kind of. We don't actually need to do that here, but you certainly could.
Making the function.
You certainly could. You could break it into parts and say, here's what f of x equals 2 for x greater than 0, and here's what f of x equals 2 for x less than 0, and together the whole thing is 1-to-1 onto and continuous in both directions. Or, do you have an idea, Jose?
So, since both are using the same topology, could you just use the identity function?
Well, the identity function won't be onto. Because if you just use f of x equals x, you're only going to get the numbers from -7 to 7. Yeah. So let me ask you another question. I know you want to say. I know you want to tell me so bad.
I think I have something. So could we show that there is possibly a transitive homeomorphisms through -7 to 7 for -1 to 1, and then we can show that like possibly a sequence for
Something
like
for
1 over
negative.
n or something for our infinity to negative infinity.
Okay, so an intermediate space
Right.
that this one is homeomorphic to.
Oh.
What if I, and -1 to 1 would be fine. I'm going to,
0 to 1 maybe.
so which one were you going to use?
Oh, I wasn't. I have a function straight from -7 to 7.
Oh, why don't you tell me your function? I'm just dying to know.
Oh, okay. It's a fraction, so I wanted, if you plug in -7, though you can't, I want to essentially get negative infinity. If you plug in 7, I want to get infinity.
Okay.
So I have a function on the bottom. I have x minus 7 squared, so now it's always positive, times x plus 7 squared on the bottom. Sorry, that's still on the
Oops.
bottom. It's a big bottom.
X minus 7 squared,
X plus 7
squared.
squared, and then just x on the top. That way I can get the negatives for when you plug in negative values. It'll be negative. When you plug in positive values, it'll be positive. And the only two domain restrictions are -7 and 7, where you would get negative infinity if you plug in -7, which we can't, so we're good. And you get infinity when you plug in 7.
So
And since those are the only two domain restrictions, this is a rational
if I
function.
if I
it's
graph
continuous.
this if I graph this function, f of 0 will be 0.
Mhm.
Okay, and f of a huge number, well, if I plug in if I take a limit as x goes to infinity, which one wins, the numerator or the denominator?
What was
Which
your
one's
question?
which one wins if x gets really big, the
Bottom.
numerator or the denominator?
Denominator.
The denominator, and when the denominator wins, what that means is that the fraction is approaching
0.
Zero.
0. So this graph, I don't know what it does exactly, but it's going to eventually go like that. And I'm
But at
concerned.
What happens at 7?
So you have a vertical asymptote at 7. It'll blow up somehow, right?
Up to infinity. And it'll continuously go up to infinity. Since if you take the derivative,
Okay.
it's always positive on that side.
You took the derivative of that?
No, I'm a 150 ASI leader. I've seen functions like this. You can do
Okay.
it if you don't believe me.
I would need a couple minutes to figure out the derivative of that, the quotient rule and everything. Anyway, so something like that. And then if you take a number just slightly bigger than 7, isn't it just going to be...
Well, you don't have, that's not our,
It's not an A.
it's not an A.
Oh, that's right, that's right.
We're good.
We're only looking at this much of it. Okay, and so then you
This
sort of have something like this over here.
Mm-hmm. It's 1-to-1, it's onto, and by 350, it's continuous.
It's definitely continuous wherever it's defined, which is throughout that entire interval, and I think you're probably right that you could take the derivative and it's never 0, essentially.
Yep.
So that therefore it is 1-to-1. It has no maximums or minims. I think that's very clever. I think that actually works. I had a slightly different function, but that one I think that one would work. What does this function kind of resemble?
A quadratic.
X cubed.
Or cube, sorry, cube.
A cubed function or
Is it a tangent?
Tangent?
Or
tangent?
Yes.
That's what I was looking for. I was about to say
Clever.
if I had given you this interval like this,
Mhm.
then you would have probably thought of it. You would think, oh, that's going to be the tangent function that goes from here to here. But then I changed this on you a little bit.
Mhm.
So
And proved any A comma B is homomorphic to C comma D, so it didn't matter that we change it.
right, you could do this. You could say this is homeomorphic to this interval. This was homework, right? You can cite homework problems and say this is homeomorphic to this one, and then you can say this one is homeomorphic to the real numbers, and for this one you could just simply give the function. So the function here that goes from -pi/2 to pi/2 to r is just f of x equals the tangent of x. Now the tangent of x is not a 1-to-1 function if I take the whole domain of it. But if I limit it to just one branch, just one of these swipes, one of these arcs up here, then this is a totally 1-to-1 and onto function. Right. So this works. If anybody was wondering how you can do it directly, without having to go through this intermediate step, you can do that. You just have to tweak this tangent a little bit. So instead of just tangent of x, if you want to go directly from here to here, you can do it by taking the tangent of x times pi over 14, as it turns out. I spent 60 seconds and thought that through. If you try to plug it, basically the -7, when you put it in for x here, gives you like negative pi over 2. And when you put a positive 7, it's like pi over 2. So you're essentially getting that same onto effect of this, one branch of the tangent function. So this would be a great question to I would just ask you to give me the homeomorphism. Okay, remember your approach to the in-class test has to be a little different than the approach to the take-home test. The questions are not going to be as hard. I'm not going to be asking you to do as much. It has to be something faster. So probably a question like this, I'm not going to ask you to take an arbitrary open set here and figure out the pre-image. That's going to involve inverse tangents and all that stuff. It's going to be messy. So more likely I would just ask you to give me the homeomorphism. Okay? What do you guys think? Do you think you could come up with this one?
No.
No? I could have made it even harder. I could have done this. I could have instead of -7 to 7, I could have made it from -5 to 9. And then you have another step where you have to, so I'm making it harder and harder to see the tangent function. And now it looks even farther away from this kind of an interval. You first have to shift 2 units over. So this one, now you would have to say -5 to 9 is homeomorphic to -7 to 7 by subtracting 2. Your function is just f of x equals x minus 2. Then go from here to here, and then go from here to here, you see. So
we already know that any open intervals in real number are homeomorphic though.
Right, exactly. But I'm just saying, if I gave you this problem on the test, and you see this interval, you probably don't think of the tangent function. Right, but if you see this interval, you might think of the tangent function, or you might think of what she came up with. But if you see this interval, you definitely think of the tangent function. So it's what I'm saying is it can be, a very simple step away from something that's obvious, but it can be tweaked a little bit. So anyway, just something to keep in mind. Okay. Yeah, you can just cite the fact that any 2 open intervals are homeomorphic, any 2 closed intervals are homeomorphic. No problem with that at all. So that's totally fine. Okay, do you want to try one more of those? Let's do another one. Okay. We're here again. It might be worth just taking a little bit of time and just thinking, before I go on to part B, just thinking about, okay, so I know that R is homeomorphic to -pi over 2. Just build yourself a little library between now and Monday. Build a little library. You know that R is homeomorphic to this. You know that any AB is homeomorphic to any other interval, so you can basically make it homeomorphic to 0, 1, okay? And you might think about, well, what else could, so this is the whole real line. These are all finite intervals. What else could you have? Well, you could have just the positive real numbers, right? And so, is that homeomorphic to R? And the answer is yes, and then you just have to think, well, what's the function that would do that? Oh, I know what it is. It's just the exponential function, for example, right? So if you take any real number and you exponentiate it, you're going to get a bijection with the positive numbers. Okay, guys, I'm really serious. This is something I would want you to be able to do. If I ask you to show that 0 to infinity is homeomorphic to R, I want you to be able to think of this function. Okay? Or even just 0, 1. So then 0, 1 with 1 to infinity, right? I mean, this one, the best way to do this one is to just take the reciprocal function like that. That's going to be a beautiful homeomorphism. This one you could get away with, trying to, first of all, just map 0, 1 to 0 to infinity or something. Well, you could map 0, 1 to R, okay? And then from R you could go to 0 to infinity, and then from 0 to infinity you could go to 1 to infinity. By the way, how would you do that? What would be the how do you prove these two are homeomorphic? Can you give me a function?
Plus 1.
Okay, that was very easy. Yeah, that works. It's a great example. But guys, I could ask something like on the in-class test. This is like a reasonable 5-point question or something. So it's worth being able to do these. So just maybe spend a little time. Also, you know, if I ask you to do something with like, I don't know, negative infinity to, I don't know, to -1. Well, this one's really easy. If you just want to do something like that, you just take the negative of the, so f of x equals -x. Okay. So just these are all just simple little functions that you're using to show that these kinds of things are homeomorphic. At the end of the day, every open interval and every open ray and the whole real numbers, they're all homeomorphic to each other. But I want you to be able to actually write down a basic little function. Okay, so that's kind of the point. And the best one to do the real numbers with a finite interval is to really do the real numbers with this via the tangent function, and then use the fact from the homework that any two open intervals are homeomorphic. Okay, so it's good to kind of keep that in mind. So just spend a little time, you know, because I don't want you guys to mess up on that part, because those are going to be like things that you've seen before. It's just I'm just asking you to write it down again. You know, give me the function that shows that. But then I could ask you something like this, which this next one, which is, I guess this is part B. Was the first part A?
Correct.
Yes.
Okay, good. So this one now is going to be like a different problem. Like this one, you haven't seen before anything quite like this. So let's take A to be the set of x, y in R squared such that 1 is less than or equal to x squared plus y squared is less than or equal to 4. And this is going to be with the Pythagorean topology, or metric, if you want to just think of it as a metric space. Okay? And then the set B, which I want to know if these are homeomorphic, this is going to be the set of x, y, and z in R cubed, such that x squared plus y squared is equal to 1, and z is between 0 and 1. Also with the Pythagorean metric. So we use the same Pythagorean metric in both cases. So now this would be a little bit harder one, because we haven't really done one quite like this one before. That's what I'm saying. I don't want you to mess up this. This is over here is old stuff. This one is a little different. What would you suggest I do first?
Draw the spaces.
Draw a picture of the spaces, absolutely. So the first space, A, let's look at that. What is that?
Is it a washer?
Yeah, so the set of points in the plane, x squared plus y squared makes a circle, right? And this is really, the lower bound is creating a circle of radius 1, and the upper limit is forming a circle of radius 2. Exactly. So what I could do is just draw that to help myself out. It's just going to be this annulus. Okay, so that's the set A, that's the shaded region. It looks kind of like that. Okay, now let's try and figure out what the B looks like. Now for B, we have to use R3, so the picture is a little harder to draw. Put my axes here, X, Y, Z.
Just a curve.
I'm going to be teaching multivariable calculus again next semester, so I got to start drawing my pictures again better. That class, you really have to have good drawing skills. What is this the graph of?
The curved surface of a cylinder.
Cylinder.
Yeah, it's a side of a cylinder, right? So and it's a cylinder of radius 1, yeah. So and it starts at the xy plane, and it does not include the bottom of the cylinder, because x squared plus y squared is only equal to 1 on the edge of the circle, and it goes up 1 unit. So this is z equals 1, and this is z equals 0 in the xy plane. It's just the side of that cylinder. So literally, it's just this white paper right here. It's literally just this. So what we're asking is this just the surface of this white paper, is this homeomorphic to this annulus right here? And if so, we're going to try to create a function that would do it. So let's give everybody a minute to think about this one.
You were going to ask me some questions that were going to come.
What class is this for? Yeah, probably this isn't going to be a very good time because I've got a lot going on today. There's lots of rooms that are open upstairs. I'd rather not have to use my office. Pardon? Yeah, just longer about that. Sorry about that. Okay. We're just using the Pythagorean metric, so that means that there's nothing weird about the open sets, really. I mean, the open sets are just going to, for example, here, the open sets are obtained by just taking disks and intersecting them with the annulus, right? And just everything that you can get that way. Make sure you're very comfortable with the subspace topology, how that works. So we're adopting the Pythagorean topology on R squared. We're adopting that and applying it to this subspace. So that means the open sets in capital A are just this picture right here intersected with, so I could draw, any disk. Here's a disk right here. So then this right here, which is partially dotted and partially solid, is actually an open set in A. Okay, so things like that. Okay, so what do you guys think?
I want to use a ratio. What ratios to do? I think it's helpful drawing them on the same graph, because right now you can draw A on that lower graph of where B is.
I can draw the annulus down there if I want to.
And then you can see how we might be able to just shift points upward.
Okay, I'll do that in just a second. I want to remind everybody, if you're not sure if they're homeomorphic or not, think about topological properties that these spaces might have. Now remember that both of these, because we're using a metric, these are metric spaces. Remember that a metric space is always normal. I believe that's one of the 5 proofs.
Yes.
So you should definitely know that fact. So if a metric space is normal, that means it's already going to be T4, T3, T2, T1, and T0. So both of these are T4, T3, T2, T1, and T0. You're not going to find any difference there. And, they're both connected. They're both, infinite sets that are kind of the same size somehow. I'm trying to think. We haven't really talked about compactness yet in terms of, I mentioned briefly the Heine-Borel theorem, but I'm not going to be asking you about that on Monday. That's the one that just says that a set is compact if and only if it is closed and bounded. And both of these are closed and bounded within the Rn that they live inside of. So they're both compact. You don't have to know that yet, but they are both compact. So all of these topological properties seem to be shared by these two spaces. That's kind of what my point is. So then the question would be, could you even think of a function that would, take 2 points here? So you would take some point xy that's in the domain of A, and then try to give me something on the side of the cylinder. And this might be where Cheyenne's suggestion comes into play. This center circle right here of radius 1 is exactly this circle right here of radius 1. Now the outer circle, which has radius 2, could be drawn on the same picture as another annulus or as another circle in the xy plane. So I think this is what Cheyenne was saying, is you could draw that annulus, that 2-dimensional annulus, in the xy plane down here, and then maybe that helps you to see how you could take a point like XY
Project
and
around.
figure out where to put it on the cylinder. Jason?
I don't know quite how to write it, but what I was thinking was because we have disks in themselves, we could basically partition A into an infinite amount of disks
Of these circles,
and
right?
stack them. And then each time we
That's
have
exactly right.
to go up, we just constrict it.
That's exactly what you do. You basically, you break this annulus into a bunch of individual circles, and each one of those circles gets mapped to a circle somewhere along the side of the cylinder. So for example, the smallest circle right here just goes to the smallest, just goes to the bottom of the cylinder here, right? And then as you go out away from the smallest circle, on this picture, what you do is you go up in the z direction. So any point that is on this circle way out here, the largest circle, will get mapped somewhere up to the top of that cylinder. And you essentially just keep the x and y coordinates the same. So like this x, so right here you have a point xy. Where am I going to map it to down here? How am I going to make a function? And remember guys, I'm probably not going to ask you to check that it preserves pre-images or open sets or anything. I'm just going to ask you, can you write the function? That's all I would want to know for the in-class test. So the answer is, you just kind of keep the x and the y the same. Now you have to be a little careful about that though, because the x and the y, once you've moved them over to the set B, the first two coordinates have to have the sums of their squares adding up to 1. So as it is right now, that may not be true, because look, this point xy is farther than 1 unit away from the origin. So how can I, without changing sort of the angular direction of this point xy, how can I actually make sure that these two coordinates are really going to have a radius of 1? I'm not even looking at z yet. I just want to get the x and the y part right.
Is it possible to have x squared plus y squared divided by 4?
Well, it's going to need to, you're not going to be able to divide by a constant. Because it's going to depend on what x and y actually are. What x and y actually are.
So like x squared over x.
Divide by
R.
r. What's r?
Radius.
The radius. That's it. That's it. I'm going to make these first two coordinates. I'm not going to change their relative ratio. I'm not going to change their direction around the unit circle, but I'm going to shrink them down, and as Alice said, I'm going to use the radius. The radius, or the distance from the origin, is just the square root of x squared plus y squared. That's it. Like if you check this squared plus this squared, you'll get 1. So that means that at least the first two coordinates are satisfying the requirement for set B. Now the last part of it is that the z value has to be between 0 and 1, and what we said, let's think about it for a second. We want the z value to be between 0 and 1, and we said that this was Jason's idea, depends on which circle we're on. Go ahead.
So because we have a thickness of 1 in there, we could just use the radius minus 1 then, because it's limited between 1 and 2.
That's it. That's exactly right. You just subtract 1 from whatever the radius is. So the radii of any, or the distance of any point in the annulus from the origin is somewhere between 1 and 2. So if I'm on the inside circle, I have a radius of 1. If I'm on the outside circle, I have a radius of 2. But we need to create a z-value that is not between 1 and 2, but rather is between 0 and 1. The way to do that is to just subtract 1 from the z-coordinate. Works really well. It works really well. This is a little tricky, and I'm certainly not trying to say this is the only way to do it. You also, remember guys, with homeomorphisms, if you don't like thinking about the picture this way, you're always welcome to try and define